How's everybody doing today? I thought it would be a great time to show you how to code an FPGA to be a frequency counter. This was a project that we'd done in school. It was like a mini project. This was a long time ago. I did it on the Basis 2 Digilent that you can see right there. I'll show you the actual frequency counter parts in this video. I may break out a different video for the BCD, which would take that frequency count and change it into a binary or change it into an actual number that can be played or displayed on the 7 segment there. So I may break this into 3 different parts, and I'll just record 3 different videos. So this will be the frequency counter video for that. Keep an eye out for the BCD video, which is binary converted to decimal. And there'll probably be a 7 segment display video following that. So this picture that you see here was the actual frequency counter that we had running. To generate that frequency, I think I used my my Rigol oscope that has a frequency generator on it, and then of course use that to check the actual number coming out of the code that I'd written. What you see here is a board that is set up just as it comes from the manufacturer doing the count. Ultimately, we actually added a crystal to this to get a much more accurate and more precise frequency from this design or this board. So I will show you how to go through, and I think in one part you'll see it's 50 megahertz that I'm using, and there may be other parts that show a higher frequency that was the actual crystal. All the links for the products and stuff like that will be below, so that you can pick that up if you want to. With using the onboard crystal, the frequency wasn't very precise. We tended to get a lot of floating in the crystal, and when the crystal's floating, you know, when you're doing divisions, you don't get the proper timing on the thing. But we'll kind of get more into that here in a little bit. So if you look at the top left here, there's the start box. This is where we initialize into, or we actually start the program that's on the FPGA. It moves into kind of an initialization box, which is not included in these loops. And I tend to put these dotted lines and stuff to show loops that are happening throughout. You've got your inputs and your outputs outside of the loop, and the loop kind of keeps going always at the positive edge of the clock. So the first thing we do is initialize everything to 0, right? So we initialize count to 0, a frequency counter to 0, and the frequency out to 0. So everything is going to start out fresh at 0. Then we go in and we add 1 to count. So this counter over time is going to actually keep track of our time with respect to the clock. And the clock is something that's in the known universe that has an actual time behind it, right? So it's a 50 megahertz clock in this actual example. And that 50 megahertz, you know, you do 1 over and you can tell how many cycles per second or whatnot. Well, 50 megahertz, which will be 50 million times per second, right? So that's an actual tie to the world of time as we know it, right? So this clock is going to be our counter that connects us to time. So every time we go through this loop, you'll notice that we go through this one box here, which says count equals count plus 1. And all we're doing is counting up, and we're keeping a total of that count. Now we're going to move from that box into, is the old signal the same as the new signal? If it is, then basically the clock didn't change, right? Or the frequency input coming in from this box up here didn't change from a 0 to a 1 or a 1 to a 0. If there is no change, we go this way. If there is a change, then if they're not different, then we go this way. If they are different, then we go this way. So if they're not different, we're going to say, is the count equal to 50 million, right? And so 50 million has to do with our frequency or the clock frequency, which is 50 million, right? 50 megahertz. So if it's not 50 million, we're going to go through and say that the old signal, which is the signal before, is equal to the signal that we just read, right? So the signal that's coming through right now from this box will be the old signal. Then we go through and we add 1 to count. Now that means that another tick has gone by from our clock. So we add 1 to count, and then we say, again, is the signal different than the old signal? Okay, so if all of a sudden we see a falling edge or a rising edge, then the signal will be different from the old signal, which is coming in from here. So this new signal will be different from the signal that we previously put in here. So if it is different, then we're going to go this way with the loop. We're going to say frequency counter equals frequency counter plus 1. So we're just going to add 1 to the frequency counter. Then we're going to go through and say, have we hit 50 million cycles yet? If we haven't, go through this loop again. And what it'll do is keep going through here. And every time there's a rising or a falling edge, it'll add 1 to the frequency counter, right? Until we get to this 50 million cycles. Once we get this 50 million cycles, we know that 1 second has gone by because it's 50 megahertz, 50 million cycles per second. So we've got 50 million cycles gone by, and we take this frequency count, which has counted every positive and negative going edge, and we go this way once we hit that. So once we get to the 50 million cycles, or 50 million count, we go down and we basically say that frequency out, the output, is going to equal the frequency counter divided by 2, because we were counting every positive edge clock and every negative edge clock. So because we're counting both edges, we would actually get twice the frequency, and we only want the actual frequency. So we're going to divide that by 2. And I'll show you here in a second how we can easily do divide by 2. Dividing by multiples of 2 is going to be very, very easy and quick on FPGAs. Dividing any other way is actually going to be a lot tougher to do. And you'll have to go through the actual division combination, right? So you're going to have to go through the actual gates and stuff that it would take to do a division. Once we make this frequency out, frequency counter divided by 2, we're going to output that here. Then we'll take frequency, or we'll take the count, bring it back to 0 so we can count another 50 million. And then we're going to actually take, this was a mistake, this should be frequency counter. We're going to take frequency counter, we're going to make that 0 as well. And then we're just going to go back into this loop here. And we're just going to keep doing that. And every single second, it'll change. And it'll tell us what the actual frequency output is by counting all those positive and negative going edges of the actual input, right? So there will be a circuit that has to go from what you're actually measuring into the FPGA. Now, if what you're actually measuring coincides with the voltages that are on the FPGA, you can probably get away with just using straight into the actual FPGA. Hysteresis on the gate shouldn't matter here because we're counting an up and a down, and we're counting a total number of those per second, right? So you could, if the voltages match, you could just bring that signal directly into the FPGA. Though in any case, you really ought to buffer that signal somehow with maybe an optocoupler or something, just to keep your FPGA safe from the outside world, because usually FPGAs are not cheap. Although you can get them pretty inexpensively now, they're still not what one might call a cheap device. So that's kind of the entire program all packed in this loop here. This is the first program that was built for this. We'll show you the next program after all this, which is actually goes through after we'd done this. We'd found out there were a few things that needed to be changed and messed with in order to make this frequency counter a little bit better at counting frequency and holding an actual number, and as well as more adept to the project that we were going to be doing with it. So what I was talking about earlier, the divide by 2, this can actually super easily be done as long as you don't care too much about the precision with an easy, simple shift, right? So we shift by 1. So in the case you see here, we have a number, a 4-bit binary number, which is 1110, and that number equals 14, right? So we got 8, 4, and 2 makes 14. Now, if we take that number and we make it equal to itself shifted by 1, we're actually going to take that 1110 and we're going to shift it over by 1, shift in a 0 on the outside, and 3 1s. The 3 1s move over to the right. Now that number is 7. So 14 divided by 2 is 7, and that's how you divide by 2 in this example, right? Super simple, super easy, super quick. So for our purposes, it works great. Divide by 2. You can divide by multiples by shifting by multiples of 2 by shifting more than once. I encourage you to go look at that. Just play with it on paper. That's what I usually do. You know, if I shift it once, what does it do? If I shift it twice, what does it do? and that'll help you understand the world of division and multiplication from a beginner standpoint, right? Because when we do these ALUs where there's like multiplication and division and stuff, most of the time you're talking about operations where you're shifting and adding and stuff like that, and it always begins with something like a shift or the shifting within the process. So I just kind of want to bring that to y'all's attention, how to shift by 2 or divide by 2 by shifting to get our actual frequency. If you remember right, our frequency was double because we were counting both the positive going and negative going edges of our signal input. So we just need to divide it by 2, so we shift by 1. So let's go ahead and do a code review, show you guys the actual code that goes with that chart. See if I can pull it up here. Yeah, this guy will do it. So we kind of go through this line by line. Let me see if I can maybe... All right, that'll work. So I'll zoom in a little bit so we can actually get a good look at this. So your normal thing, we've got a module top. We show our inputs, clock and signal, and a frequency output. As you'll see later, ultimately this was put into a bigger project, and I'll give you all guys a block diagram here in a little bit. So as we talked about before, you know, this is going to be a sub block within other blocks because we actually export this to an LC or a 7-segment display so that you can see it. But that doesn't matter because this will work just fine. I call the top module here just because this was what I was working on. Somebody else was working on BCD and somebody else was working on the 7-segment display. We all made our own top modules, then we imported them into one project, made a new top module which instantiated R3 and tied them together. So this is kind of just your normal module, which you might think input signal and input the clock, and then we're going to output the frequency. We're going to need a few registers here. We're going to need mainly all counting registers, right? So we're going to need 3 different counting registers. We're going to count the frequency. We're going to count every time there's a cycle, right? Every time there's a cycle on the clock. And then we're going to have a register for showing the frequency output. And then we'll also have a register that gives us, you know, the old signal. So we see the signal coming in. Was that a 1 or a 0? Okay, the old signal was a 1 or a 0. Did something change? So then we'll assign frequency to equal frequency out, which is basically just saying we want to tie this register frequency out to our actual output, which is frequency. This is a pretty simple code. You know, it takes a little bit of thought to get through it, but it's not that bad. So initially, the first thing we did, as we said before, we come in and we make all of our registers 0. So we've got a count at 0, our old signal is 0, our frequency output is 0, and our frequency count will be 0. And this just gets run once. So when you make an initialization block, it just runs that very first time when it goes through. If you want to rerun that, you have to reset the FPGA. You could tie this to a button, right, and just rerun the initialization on a button. You could tie it to an input or a different signal or whatnot, whatever you needed to do for your purposes, right? Then we've got this always loop, and we're going to check the positive edge of M clock. So every time that there is a positive edge of M clock, we're going to begin. So then we're going to say that count equals count plus 1. That's outside of everything else. So count will always equal count plus 1. That count will continue to count, which we spoke about before. Every single time that this loop here, which is that big loop that we saw before, every time this happens, count is going to increase. So every time that there is a positive edge of M clock, count will increase. So this should increase. If we have a 50 megahertz clock, it should increase 50 million times per second. So from there, we go through and we say, we talked about earlier, is the old signal the same as the new signal? If the old signal is not the same as the new signal, then we'll get a 1 here. And if we get a 1 here, then we're going to add 1 to the frequency counter. Otherwise, it's just going to go and skip this step. So if the old signal is the same as the new signal, then we'll skip this, and we'll go to the next if. Now, every time, whether that's the same or not, we'll also do this if. We're going to say if the count is 50,000,000, which is our 50 million. If our count is 50 million, then we're going to take frequency out, and we're going to make that frequency out frequency count shifted by 1. So basically, we kind of did this all in one step here. We're taking our frequency count and shifting it by 1. to divide it by 2. And we're going to make that our output. And our output will stay that until the next time we change that output. Then if count equals 5 million or 50 million, remember, we went through and cleared all of our other variables. So we made count 0 so we can count up to 50 million again. And we made frequency count 0 so that we can do a new count on the actual frequency input. Then after all of this, we just basically tie our old signal to our new signal, and that basically refreshes our old signal to be what the signal was when we started in this loop. And the next time we go through this loop, we can check to see if our old signal is the same as our new signal, or our new signal is the same as our old signal. So that's the quick and easy code to do this frequency counter. It actually worked out pretty good, but it was floaty, and there was a lot of little issues here and there. So we went through and did something else with it. So let me not add that. We'll close this out. So if you made it this far, thanks for sticking around. I'm going to make this video a little bit longer, but the rest of this video will be good to show you how to fix one of the biggest errors that we were having, and it helped us to get a more accurate, stable reading from our code. So that was the first code review. Now, what we wound up doing is to average the output frequency. So we kind of averaged it to say what is this actual frequency over a very short span, or over a little bit longer of a span actually, because the frequency was just jumping all over the place, right? Because the frequency input was moving around a little bit, and the clock was moving around a bit, and it was just too fresh of a signal. So we decided to average the signal, and this is the flow chart for the actual averaging of the signal. So with the sample averaging, we need to average where we wanted to average all the signals together. So we watch count, only this time we're only going to watch it every 16th of a second, which is actually that count number, the binary of count, shifted over by 4. So if you shift it over by 4, you divide it by 16, which at the 50,000 we were looking at gives us, or 50 million we were looking at, gives us 3,125,000. So if that count is 3,125,000, then we're going to go in and we're going to increase this new counter called average counter. We're going to increase that by 1. And average counter is from 0 to 7, right? So every time average counter goes up, we're going to do a case on average counter. And the case is like a bunch of if statements. It's just easier to write out, right? So in the case of average counter from 0 to 7, whatever that average counter is, we're going to put this, the frequency count, we're going to put that into a placeholder, right? And we're actually going to shift frequency count over to divide it beforehand to put it in there, which we'll talk about a little bit more here in a second when we look at the actual code. So what we've got is, it's kind of like a rolling set of registers, if you will. There's 0 through 7 registers, or multi-registers, right? So blocks of registers. And each one, every time average counter moves up 1 tick, we're going to put the actual frequency count into that register. So this register bank will store the frequency every 16th of a second, right? So every 16th of a second, we're going to put a new value sequentially into these registers one by one. And then we're going to take the actual frequency out, and we're going to, at the next 16th of a second, we're going to put that into this output, and the output is the average of the frequency old, or the old frequency holder, which is frequency out, and the bank of frequencies here. So we're going to look at how to do that in the code when we get there. But before we do that, there's another problem that we were having that we wanted to address, and that is debouncing. And I've talked about this in other videos, but I just kind of want to go over it really quick. What we're doing is, when there's a signal that's coming in that may or may not be one, it's kind of bouncing. Like if you've got a button and you touch the button, the electrical contacts kind of click on and off until it's fully depressed. Well, with the signal, there's hysteresis, and there's a line in the, there's an actual line going from whatever the signal is coming from to the FPGA, and there just may be some noise that makes this actual signal read a 0 or 1 when it's kind of like a false 0 or 1. So what we do is we filter it by saying we want to wait until this thing is fully positive 1 for a very long time before we actually make it say that this is actually a 1 or the clock has actually come up, or sorry, in this case, the signal has actually come up. So what we're looking at here is kind of a way of doing that filter, right? So what we do is an AND of this entire register, and this would be a bitwise AND, right? So it's going to look at all these and it's going to combine them and say, and this and that and that and that and that and that and that. So with an AND, you have to have all ones to get a 1 with an AND, right? So if there's any 1 in here, or if there's any zeros in here, it's going to make a 0. So if you AND this whole thing together, it's still 0, which is what we're doing. We're saying this is still 0. We ANDed all this together, and there's a couple 1s, but it's not fully 1, right? With the same one, it's getting closer, right? There's a bunch more 1s, but it's still not fully 1. So as this is kind of the signal as it shifts in. There's still some zeros in. There's still some zeros in. This next one is all 1s, which is when we get to this point here on the wave. And if it's all 1s, when you do an AND on it, it'll equal 1. So this last bank here is just, it's a negation of the filter. And it works in a different way, and I encourage you to look at that. Maybe draw it out on paper. Think about what happens when a 1 comes floating through, or a bunch of 1s, or if it's all filled with 1s. So let's go ahead and look at the code for this. This is it's the same idea, same concept as the previous code, but this is with the filtering and with the debouncing in there, right? And this is the code that will actually be on GitHub. If you want to go ahead and go download the code, this is the code that'll be up there. So we start out with frequency counter. This is our module, same as it's always been. This is our module start, right? So we have to name our inputs, which is the clock and the signal, and then we have to name our output, which is frequency. The reason that you often see that this says like mclock, and this is why I keep bringing this up, is that this isn't the top module in our final design. So we're passing clock off as something else, and we pass it into this. I call it mclock just to remind myself that this isn't the actual clock, this is the clock passed along from somewhere else. So that I could, in theory, put some other clock in there or put some other signal in there. But it's just kind of a reminder for me that this isn't the actual clock in the program. This is a passed along clock from top. So we've got the inputs in clock and signal, and we have the same output, which is frequency. Now there's a whole lot looking like it's going on here, but essentially it's the same exact thing, only we sub in the loop that I just showed you, which is averaging, and we also do some debouncing. So we need a lot of registers to do this debouncing. So we've got our original frequency count, we've got our frequency out, which is going to tie directly at some point, and one of these guys will tie directly to our frequency output. And then we've got all those registers that we talked about. We've got register 0 or register bank 0 down to register bank 15. Next, you see we've got a count register. This is actually pretty good commented code, so you can go through and read kind of what each thing does. This register is used to create a count timing, so that's our normal count. It's going to be counted every single time something happens. The old signal, which we talked about before, will change every single time, and we'll be able to compare that to our new signal. Debounce signal is going to be a 4-bit register, and we're using this register to actually debounce the signal as we talked about. So avclock is a new register that we'll use in the 16th averaging timing thing. And then the frequency temporary, that's our temporary holder for the frequency. And that's going to be a little bit larger because of the way we're pushing in all these numbers. We don't want to lose any information. So when you'll see here in a sec, but when we add everything together, it winds up being a bigger number or a bigger bit number. And we want to keep that information before we go through and do our shifting to divide it out. So here's our initial block. This is what happens at the beginning, right? So we initially start with doing this, and it only happens at one time, as we talked about before. So we've got our count, we set it to 0, our old signal, frequency out, frequency count, avclock, all of our frequency banks and our frequency temporary. We're going to set all those to 0 just to initialize, because you never know what starts inside of those registers. They could be floating. They could be 1s, or they could be 0s. It could be anything while it's sitting there and when it just starts up, right? Then we get to our always loop. This loop's a bit bigger compared to the previous one, but it's mainly because we're just adding that averaging in. So as we said before, every time we get M clock, we're going to count. So we're going to add 1 every single time, same as before. And then we're going to shift in the signal into this debounce signal, which is what we were talking about previous with debouncing the actual signal. So every time the clock ticks, we're going to say that the very last bit in that debounce signal is signal, and then we're going to shift it over by 1, and we're just going to kind of keep adding that signal onto the end of this guy. And then we're going to do this next if block, which kind of surrounds everything. If you can see, there is no end statement until down here, I think, for this guy. So then we use that. We use the debounce signal, and we say if and debounce signal, which is what we were talking about, and or not debounce signal, begin. So the reason that we do this and then the not and we're oring them together is to say if there is all ones or all zeros, then we're going to go ahead and start, and this will do the if statement, right? So once we look at this actual debounce signal, we're just going to use that to say, do we want to actually look at frequency now or at the signal now, or should we wait? So if we have either an all ones or an all zero, then we can look at the signal and we can say, is that signal the same as the old signal? If they're not the same, then you're going to want to add 1 to frequency count. This is the same thing we were doing before, it's only now we're doing it with a debounce signal. So with this next block down here, this is if count is greater than or equal to count 2 shifted by 4. Now count 2, we didn't talk about. We'll go back up here and look at count 2. So count 2 is an actual parameter that we set up. So it's kind of like a hard set variable. Count 2 is going to be our actual frequency of the clock. So we're still looking at that 50 megahertz clock. And what we're doing is shifting that over by 4, which we talked about a second ago, is the 3,125,000. So if the count has gotten above that 3,125,000, then we're going to take frequency out, and we're going to make it the frequency count shifted by 3. So what we're doing here is dividing beforehand. We're shifting it over, and then we're going to do count to 0, frequency count to 0, and we're going to add 1 to av clock. So we're resetting the count and the frequency count, but then we're setting av clock to the next av clock, right? And this av clock is what we're going to use in our case statement. So every 3,125,000 seconds, we're going to add this frequency out, which we shifted over to this bank of frequencies, which is 1 through 7, or 0 through 7, which is 8 frequencies, right? So then we take that value and we put it in here, and we wind up filling up this bank over time, and then if we get to the 7th position, which will be 8 times of happening, and once that happens, we can update our actual frequency, right, on the output. So now we're going to take this is basically the same thing as these up here. We're just going to go ahead and shift in a new value for the 7th register. But then in here, what we're doing is we're going to say the frequency temporary, this is a temporary holder for the frequency value, is going to equal all 7 of these added plus these down here added, which we'll look at here in a second. So I'm just basically adding all those together. And when I add all those together, I need a bigger register, as we talked about before. Then the default is basically just to do nothing, but you always got to have a default in there, and then we end the case. Now we're going to do what we had done before. We're going to make old signal equal to signal so that we can compare the two. And now we get to these registers here. And what we're doing, we're saying all of these registers equal all of these registers over time. So these registers over time are going to get put into here, but these are held over for 1 second. So what I'm doing is I'm taking all these values that are held over for the, not 1 second, sorry, these are all held over to the next clock. So I'm taking all of these guys that are over here. When this happens again, these guys will be held back, and these are fresh, and we added them all together. Then when we get to the bottom here, we see that we assign frequency to be equal to the frequency temp shifted by 4. So when we shift by 4, that's 2 times 2 is 4, times 2 is 8, times 2 is 16. So we're dividing that by 16. So we've got 16 values here, 0 through 7 and 8 through 15. So 0 through 15 are 16 values. We added 16 values together. We shifted over by 4, which effectively divides it by 16. You add 16 values together and divide by 16. you get the average of that value. Then we end the module. So if you have questions about that, I know I kind of went through it kind of skippity. If you have questions about that, then let me know down in the comments below. So let's go ahead and close that guy. I don't care much about that. And let's continue on. And all I want to do from here is show you guys what we were talking about before, which is how all this stuff kind of came into this top module. So currently what we're talking about in this video is the frequency counter. We have an input, we do the actual count, then we output that binary count. Now that binary count ultimately goes to a top module. Inside of that top module, there's a BCD converter, and that will BCD convert this count that can be used to drive the 7-segment display. And so that is like the final project that we wound up coming up with, and that's what you see on the front page. I'll probably come up with this BCD converter video later on, and then I'll come up with the 7-segment video. Just kind of keep an eye out for it. If you subscribe, you'll see when it comes out. I'll try to get those come out sequentially, but I kind of have these series going, and it tends to be that certain people like the series and certain people don't. I'm trying to get new content out, but I want to have enough content for people who do like the one series or another series to be able to watch through it. So I'm kind of doing mix and match here and there, and putting in new videos here and there. And then of course, if there's some sort of video that everybody seems to be requesting a lot, I'll pause, go ahead and do that video so that people can have that information, then go back and do these videos. Anyways, thank you guys for watching. Don't forget to love well.